All right, good afternoon, everyone. Thank you for joining us in the RC Design Concrete class on Thursday session. Before I get started, some quick announcement. We have several students asking about the homeworks. There's just one typo on homework number 5. If you read inside the homework PDF file on the left top corner, it says homework number 6. That was a typo. Basically, when I wrote it, I forgot which one that was, but later I realized that. I will correct that, but I don't think it will prevent you from doing the homework. So to speak, just clarify that. And on the last problem, the homework number 5 is to find the effective beam width. You can refer to the equation we showed last lectures on how we determine if it's L shape, if it's T shape, and that's the only equation you need to determine the effective beam width. There's no need to calculate the moment capacity of that section itself. Okay, so that's that for the third question of the homework number 6. Now, as I said, there's gonna be a lab potentially planned for this lecture. Since we're on time, we'll be able to cover most of the content so far. And just a quick heads up that the lab is probably gonna be a software design, a concrete section. So on Flexure, because we already covered that. So instead of do a manual design, we will show you how we can do a computer design using the software. For that session, I'm going to upload the notes on it potentially the week after next week during the Thursday lab session. And we will have our TA, Yanxiao Li, come in to help us demonstrate how to do a design. And of course, I'll be there if the time permits. Okay, so that will be that. So the lab design session will yield a course project, but the weight is almost equivalent to a homework. So we'll consider it as part of homework for that lab design. Okay, so any questions about what I just announced so far or course itself? Anything, folks? Anything?
Is that going to be
I
an
only got here a minute ago.
Okay, so maybe Steve, you go first, and Emily, I can explain it later. Yeah, Steve?
Yeah, will that be an in-person lab or will it be just online still?
It will be a software design lab. So essentially, we'll show you how to use software to design a beam member, and you probably can use that for your senior design class down in the road. So it's not going to be in person, it's still going to be Zoom.
Gotcha. Thank you.
Yeah, no problem. So Emily, we were just talking about a course design for lab, basically. Since we're on time, we'll have a lab session. We're going to show you how to design a member in terms of flexure strengths using the software. And the outcome of the lab will yield in terms of report. Whether it's a group or individual, we yet to see. Probably going to be individual. So that will be part of the homework to be evaluated. All right. All right. Anything else, folks? Are we okay with this setup? All right. If nothing else, let's quickly come back to the shear design session. Okay. So let me share my screen. Give me 1 second. Here, iPad. Okay. All right. So we are at lecture 13. Okay. So we're going to talk about how to design shear. And now I have to, okay, wait a minute. So why stop sharing? Okay, so while we have talked about shear design for concrete and the reinforcement part, so last lecture we focused on the concrete part and we say that VC, and recall, VC equal to a 2 lambda squared F prime C BWD. Okay, so that's the contribution from the concrete. Okay, so for shear, for steel will be a little bit different. All right, so let's continue our lecture. So lecture 13, still on shear. Okay, so on the steel reinforcement, it will be a little bit different. How different? Let's take a look at the section first. So my cracked section looks like just like this. right? And I have my steel stirrups like that, and provide me the tension that needed to stitch the concrete cracks, essentially, that is. To stitch the concrete crack. And the spacing between the stirrups is S. Spacing between the stirrups is S. So before we talk about the contribution for the shear from the steel, let's take a look at the crack. Let's take a look at the crack. Okay, so first of all, if I connect a line, okay, on the crack in the red color, and I'll see that it's roughly a 45-degree angle. Roughly a 45-degree angle. And that means the depth of the crack, okay, depth of the crack should equal to the length of the crack. Should equal to the length of the crack, D, and that is the diagonal crack. Okay, that is the diagonal crack. So why do I need this? Because now I can estimate how many stirrups can be provided in this region, in this cracked region. Okay, and don't forget my support right here. All right, so first of all, let's write down here the length of the diagonal crack, length of the diagonal crack is same as the depth, D. Okay, same of the depth D. Okay, now with this, we can simply calculate the number of stirrups. Calculate number of stirrups roughly equal to D over spacing S. Okay, D over spacing S. By the way, this S is the spacing between stirrups. Okay, S is spacing between stirrups. Now for the reinforcement, right? For the stirrups, right? So if I zoom in to take a look at here, the stirrups, right? The tensile, right? So tensile, let me just use small t to represent the tensile resistance of each stirrup. Okay, the tensile stirrups or the tensile force provided by the stirrups equal to T, that equal to AV. Okay, that is the cross section of the stirrups. Cross section area of the stirrups. Okay, and multiplied by Fy, and let's use a T to differentiate from Fy for the flexure reinforcement. Okay, and this is so-called yield strength. Yield strength of stirrups. Sorry. Yield strength of stirrups. And normally this is the same as the flexure strength. Sometimes it's not. Sometimes it's not. All right. Now, in terms of AV, which is the cross-sectional area of the stirrups, right? You got to figure that for the stirrups, it follows this U shape. And with two hooks in the top, two hooks in the top. All right. So when you do the cross-section, you actually have one leg, two legs. One leg and two legs. Say each leg, for example, so IE, or actually EG, for example, a number 3 stirrups. Okay, number 3 for number 3 stirrups. So each leg, the area of each leg equal to 0.22 inch squared. Now, since I have 2, so AV would equal to 2 multiplied by AL, that equal to 0.44 inch squared. 0.44 inches squared. Okay, so that means for each bar of the stirrup, right, I have 2 legs, and that is how much of a reinforced area I have per each stirrups. So with this, how much total shear force I can gain from all these stirrups, right? So simple. So VS, which is the shear resistance provided by steel, should equal to a tensile resistance per stirrups multiplied by number of stirrups, which is D over S. And that gives us a V Fyt multiplied by D over S. Okay, so that is the total resistance, right, for the stirrups. Okay, but keep in mind that this is for vertical stirrups. All right, meaning the stirrups is in vertical direction, right? In vertical direction. So if I draw the handlebar here, these are 90 degrees angle. 90 degrees angle. Okay. Now what if I have an inclined stirrups? Okay. What if I have inclined stirrups? Meaning if I have a crack, but for some reason I cannot provide straight stirrups, I have to provide them in terms of angle, right? I have to provide them in terms of angle. So for example, they may stick up like this, stick out like this. And let's assume each of them will still provide a tensile resistance, and the angle here is alpha. Now we don't know, let's just assume it's alpha. And don't forget, each of them will provide AVFYT. Each of them will provide a tensile resistance of AVFYT. So here's AVFYT, here's AVFYT. All right, and the same distance of the, or length of the crack equal to D, and the height of the crack equal to D. Okay, and the spacing, when we talk about spacing between stirrups, it is here. Spacing between stirrups here. All right, now given that this is support on the left-hand side end. So for this case, the inclined stirrups will provide you a different shear resistance, and that equal to AVFYT, okay, multiplied by D over S. Okay, so you see that this is the same as before, except we have to multiply an additional factor, that is sine alpha plus cosine alpha. So that is added. That is added. All right. So this is how we calculate the shear resistance by the steel, by the stirrups. Okay. So now with this known, let's kind of do a review of what we have learned so far by shear, right? So if everything's panned out like we just said, then the shear contribution from concrete equal to 2 lambda square root F prime CBD. And by the way, B is BW, the web, okay? And shear, VS, depends on the geometry, right? Depends on the shape of the stirrups, right? So now, excuse me, AVFYT, D over S, and this is for vertical stirrups. Oops, sorry, vertical stirrups, okay? Or AVFYT multiplied by D over S, multiplied by sine alpha plus cosine alpha. And this is for inclined. Don't know what happened today. Inclined stirrups. All right, so we have the contribution now from the concrete, and we have the contribution now from the steel. So the total nominal shear resistance, Vn, should equal to Vc plus Vs, right? And phi Vn, which is a design shear resistance, should be phi Vc plus Vs. And that should be bigger or equal than applied shear or factor shear, Vu. Applied shear or factor shear, Vu. Now that, ladies and gentlemen, is the design process, or is the essence of the design for shear. Okay, essence for design of shear. All right, okay. I want to pause here quickly, ask any questions? Any questions? Folks, any questions? Are we good? Okay, so if we're good, this is the basic concept. This is the basic concept for shear. Okay, so today we're going to get into the detail of the design, right? But let's be clear, there are two versions of a shear design. So ACI 318.14 and ACI 318-19. They're slightly different, okay? And they're slightly different in terms of the minimum shear reinforcement. AV min and the contribution from concrete VC. Okay, and the reason why they're different is that previous version 14 is a little bit is a little bit unconservative in some cases. All right. However, since our textbook, if you don't mind reading, our textbook is still on ACI 318.14, and most of the current design out there are still 318.14. Okay, except the new designs, and I haven't seen a whole lot yet. So we're going to introduce both in this course. And the procedure or the time sequence goes, we'll introduce the first 14 version one first, and we'll introduce the 19. And in terms of solving the homework, we will follow the 14, unless in some special cases, you have to apply the 19 criteria, which I will talk about. All right, but I want to make it clear right now. Okay, so today we're going to learn, objective is understand or familiar with shear design process for RCB. Okay, just get a little bit information out first. Okay, so 13.1, first thing we need to do is we need to talk about minimum shear reinforcement. Okay, all right, so we all know that if I have the design shear, which is phi Vn, that equal to a phi Vc plus Vs, that is bigger or equal than Vu, factored or applied shear, then I should be fine. Right? But what if I don't have to provide steel reinforcement? I jump in and say phi Vc, which is the contribution by the concrete itself, is already bigger or greater or equal, bigger or equal to Vu. That is the factor shear, right? So the question arrives at, does it mean no stirrups needed? Does it mean we do not need stirrups anymore? We can just go with concrete? The answer to that question is no. Okay, no. And ACI 14 says, and this is by 14, okay? ACI 14 requires that if, or actually since the shear failure is brittle, it's sudden failure, right? Okay, now a minimum reinforcement or shear reinforcement is required. Okay, so without any stirrups, you cannot have a section that can resist the shear. And you can find this from ACI 9.3.3. And this is applies across the board, 14 or 19, they're the same, okay? And you find the equation that, AV min, okay, minimum amount of reinforcement is equal to 0.75 square root F prime C, and BW, which is the width of the beam, multiplied by S, which is the spacing of stirrups, divided by FYT. All right, and this has to be greater or equal to 50 BWS divided by FYT. Okay. Of course, there are exceptions, right? But the few exceptions are provided in ACI section 9.6.3.1. Okay. 9.6.3.1. But this is very important. This is very important information that even when you see that your shear resistance contributed from concrete itself is already sufficient, you still have to provide minimum shear reinforcement. Minimum shear reinforcement. All right, but apart from that, things are not that bad, right? So let's take a look at the design process for shear. Okay, so how we design for shear? First, you have the applied shear force from the loading. Then you say this has to be smaller or equal to smaller than or equal to VVN, has to be smaller or equal to VC plus VVS. So VS has to be greater than VU divided by V minus VC. And the reason why we write equation like this is normally the section dimension is given. We just need to design for reinforcement. Okay. So in this case, for vertical stirrups, oops. Okay, VS, which is shear, that equal to AV FYT multiplied by D divided by S. Remember, that is contribution by the stirrups. All right. So with these two equations, I can essentially solve for spacing. So solve for spacing. Solve for S. S required should equal or smaller than AVFYT multiplied by D divided by VU divided by V minus VC. Okay, so you can see that the main parameter need to be solved is the stirrup spacing. So normally the practice goes is the stirrup size is given stirrup section size. Okay, given stirrup size, and we are here to design for spacing. We are here to design for spacing. So it is the spacing, stirrup spacing that needed, not the size. We usually pick the size. So you say, Bob, what kind of stirrups you pick, right? You say usually you already know the size. So number 3 bar or number 4 bars are typically selected for stirrups, okay? Usually we are constrained or we're restricted by the size and we're just trying to find spacing, okay? And now if the stirrups is inclined, it's not vertical, if inclined stirrups are used, all right? Now the spacing will be different, right? So the S required inclined, right, should be smaller than or equal to AV FYT D over VU divided by V minus VC, whole thing bracket, and then multiply by sine alpha plus cosine alpha. All right, and don't forget this alpha is the stirrups, inclined stirrups, right? And the angle between that and the bottom surface like this. Bottom surface like this. Okay. All right. So now that is the design process. Okay. That is the design process. All right. Now you may say, okay, look, Bob, I understand this. This is saying, okay, after you know how much contribution from concrete, you take out the concrete contribution and you divide the spacing and divide by the area of the stirrups, the strength of stirrups, and come up with the spacing for stirrups. That's fine, I understand it. But what if I don't need the stirrups, right? What if VU, right, is smaller than VVC? That means VU is smaller than the concrete contribution, right? What do? In this case, you provide minimum reinforcement for shear. That is AV mean, and we talk about that equation equal to 0.75 square root of a prime C, and this is BW spacing divided by FYT. And this has to be greater or equal greater than or equal to 50 BWS divided by FYT. Okay, but just this is not enough. Just this is not enough. Okay, in addition, because shear is so brittle and we're so worried about it, so we provide a lot of constraints. So in addition, we have to make sure at least one stirrup, okay, is provided. Okay, in the shear crack zone. What does it mean? It means you may as well calculate the spacing between stirrups, but when we put the stirrups in, observing the crack, I need at least one stirrups, right? One stirrups put in here in the middle. Okay, if this is the case, that means I need to have a spacing like this, right? So if this is a spacing, this is the crack length D, and spacing is S, that means S required has to be smaller than half of the crack length D. Okay, half the crack length D. So in the ACI in the code, okay, in the code, as required, okay, has to be lesser of, or in this case, not required, but maximum spacing, right? Maximum spacing has to be lesser of 2, D divided by 2, or 24 inches. And you can find this from ACI 9.7.6.2.2. So this is from ACI. Okay. All right. And this is not over yet. When VS, which is stirrups, contributed shear resistance, is greater than 4 times of square root F prime C BWD. All right. S max is halved. Okay. What I mean by that? That means in this case, S max has to be lesser of the 2, D over 4 or 12 inches. Okay. And this is same as ACI 9.7.6.2.2. And now here, we're done with all the requirements. All right. And that is quite a lot. That is quite a lot of requirements. I mean, you have to go all the way from concrete first and find spacing first. And then you have to consider the maximum spacing has to be lesser of these two. And if VS has to be bigger than 4, you have to consider spacing of these two. I mean, it's all over the place, right? It's quite complicated. So how do we have an organized fashion to remember all of this? Right? So here I want to present you some of the design tables. Okay, design table. So 13.3, design table for shear. Okay, just to help you remember all this, right? So first thing first, VU, which is a factor of applied shear force, has to be smaller than or equal to VVN, and that is phi VC plus phi VS. And then VS, which is the shear resistance for steel, has to be greater than or equal to VU divided by phi minus VC. Okay, that's the first equation you have to remember, basically. All right. Now the second equation, required spacing for the stirrups, then becomes AVFYT multiplied by D and divided by VU divided by phi minus VC. Okay, and then the maximum spacing means the provided spacing cannot be bigger than this is that of lesser of the following, okay? Lesser of the following. So has to be lesser of d over 2 or 24 inches. And you realize that this is essentially coming from ACI 9.7.6.2.2. We just talked about this. And this is called at least, right? And to ensure at least one stirrup in crack length D, remember? Now, the other four is AVFYT divided by 0.75 square root f prime C BW. Here, also AVFYT divided by 50 BW. Okay, you never seen this? Well, you saw this, but in a different fashion, right? And that different fashion is this fellow right here. This fellow here, remember? So this is just conversion from the AV, the minimum reinforcement, okay? AV min. Okay, and this you can find them from ACI 9.6.3.3. So you see that I convert everything back to spacing, Now, in addition, once you satisfy all this, we have to do a double check. So if VS is greater than 4 square root f prime C BWD, okay? So remember what we talk about, S max is halved, right, divided by 2. So S max now equal to the lesser of, go here, D divided by 4 and 12 inches. And this is ACI 9.7.6.2.2. Okay. So that is the requirement. That is requirement. But don't forget, right? Don't forget, you have here AVFYT divided by 0.75 square root f prime C BW, and also AVFYT divided by 50 BW. Okay, all right? Okay, and of course, this is bigger than that, so this is VS smaller than or equal to 4 square root f prime C BWD. Okay. All right. Okay. So this is the spacing requirement. Yep.
If they're half, why are we not changing the values on the denominator on those two bottom ones?
You mean these two, right?
Yes.
When we say half, it's only concerned about at least one stirrups in a crack. These two are the AV mean that will not change. Okay?
Okay.
Yeah, only concerned about this is because we want to make sure one crack in one star in the crack. This is in the case that you have too much reliance, means you have too much write-down on the steel reinforcement, right? Because this is a lot, so you have to provide at least spacing over there to make sure they're packed in the crack. Now, in this case, normally this is satisfied. The AV mean is normally satisfied already, because you can see that this is such a large number, and you usually satisfy the AV mean already. All right, but nice catch here, okay, thanks. All right, but this is not all. This is not all. There are two more miscellaneous, okay, two more miscellaneous tables. So number 5, for stirrups. Okay, for stirrups, FYT, which is the yield strength of the stirrup, has to be restricted to be lower than 60 KSI. Okay, lower than 60 KSI. Is it, what if I use a higher steel? You know, I just have all the money. I want to provide the best reinforcement there is. And for example, I provide a FYT equal to 75 KSI. You know, should I gain more out of it? No. You have to use FYT limited to be 60 KSI regardless. And this is from ACI 20.2.2.4. You can see that ACI has such a strong limitation on shear design. Okay, very rigorous, very rigorous. And last but not, yes.
After exceeds there.
Sorry, where?
What did you write after exceeds?
This example, and it's just a question mark. Okay, sorry about that, a little bit rushed. Clear? All right, okay.
Yeah.
Now, one more thing. Even if you satisfy all the requirements, after everything said and done, you have to make sure that maximum shear resistance provided by the steel reinforcement has to be contained by A times square root F prime C BW D. All right, that means your contribution from steel cannot exceed this value ever. And you can find this from ACI 22.5.1.2. Okay. Now, again, you say, okay, Bob, this is hard. What if I done all this and final step number 6, find this number bigger than that? What happens, or what should I do? If not, okay, we need to increase BW or D, increase section size, basically. Okay, so that means you rely too much on the steel. You need to jump up your concrete contribution. You need to increase your concrete contribution. All right. Okay, so this is all the theory we need. All the theory we need on the shear. All the theory we need on the shear. Okay. All right. I'm going to stop here. And this is going to be a short lesson today again, because I want to finish the shear example on Monday. So any questions for me on this, on the conceptual thing? Guys, are we good on this? We're good on this? Okay, so if we're good on this, I want to leave with a quiz, okay? Leave with a quiz. And I'll leave the homework. You may not be able to finish the homework, but you can start today, okay? But before I do, let me leave with a quiz. So I believe it's quiz number 6, okay? Check me if this is
It's
wrong.
7.
7 already. Thank you so much. Thank you so much. My brain usually farted. Sorry about that. So quiz number 7, and now this is due next Thursday. And it's a simple quiz. All right. So I have a section, and I have a stirrups sitting in here. All right. And let's just say this is number 3 stirrups. Okay. And my height of the section is 22 inches. And the width is 12. All right. And I have 2 number 9 bars at the bottom. Okay. 2 number 9 bars at the top. All right. And the concrete is a 4,000 PSI concrete. Okay. And yield strength, very low. I set it to be 40 KSI. Be careful, okay? It's not 60, 40, okay? And if I provide a spacing between stirrups of 10 inches, okay? And I want you to show me what is the contribution of the concrete to shear and what is the contribution of steel to shear. All right, so that's quiz number 7. Okay, all right, with that, I want to stop here and we'll continue on Monday and we'll go through one example, how to design shear for this approach. All right, okay, you're welcome to say if you have any questions, okay?